Good time of the day, everyone. This is Ivan from EPIC, and this is the series of online technology meetings that we run on Photonics this year. And today we have a very exciting topic that is PIC packaging and testing. Today we will hear from 7 speakers representing all the value chain of photonics industry, working with PICs. And we'll start with the presentation of Peter O'Brien from Tyndall Institute, and then Jeroen Duis from PHIX. We'll also have hear from Jochen from Nanoscribe, Jean-Luc from Photonics, and Nikolaus from vario-optics, Josue from Ficontec, and Richard from Yelo. Apart from this amazing set lineup of speakers, we also have over 80 people in the room tonight with us, and those are representatives of the companies from every chain in the value chain. So we start with people working on R&D for PICs, semiconductor manufacturers, and equipment manufacturers, as well as companies that provide lasers and optics, and all the way to system integrators and the end users of such technologies. And also very important, today I have my colleague Antonio Castelo with me. Hello, Antonio.
Hello, everybody. Yeah, welcome everybody, and it's good to be today with this nice topic and also these great 5 sponsors that are supporting the event to date. As you can see, our sponsors today are the companies PHIX, Ficontec, AEMtec, axetris, and MicroOptics. And we want to give some time to introduce the companies and to speak a little bit of what they are doing. First one, Jeroen from PHIX. The floor is yours. You can tell us what is PHIX doing.
Thank you, Antonio. Yeah, so we are PHIX, and we are established in 2017, and we do the packaging of photonic integrated circuits and MEMS-based components in different volumes. So really helping from prototype to high volume production. We're leading expertise in hybrid PIC assembly, fiber attachment, and ultra high frequency electronics interfacing. So currently we do packaging up to like 120 gigahertz.
So thank you very much. And now we have next sponsor is Ficontec, and we have today Josue Parra, that you can say a few words about your company.
Yes, thank you very much for the kind introduction. My name is Josue Parra. I'm a research and development engineer at Ficontec Ireland. Ficontec has already more than 20 years in the market. We specialize in providing automated photonic solutions for the alignment, assembly, and testing of photonic integrated circuits. I mean, all what involves, let's say, from MicroOptics, from the PICs, from different optoelectronic components, and electronic components as well. If we have to fix them, cure them, using maybe some epoxy, some laser soldering, and of course, we are focusing as well in the testing of these components that can be attached not only at a die level, but also at wafer level. Thank you.
Thank you very much, Josue. We can move to the next one, the company AEMtec. We have Andreas Freitag. The floor is yours for telling us a little bit about your company.
Good afternoon, everybody. Thank you very much for the kind introduction. I'm from AEMtec, key account manager since 3 years now. AEMtec is located in Berlin with around 230 people, and we are specialized in the advanced electronic packaging services for our customers, starting from the process development due to volume production. If you can just switch to the next slide. Yeah, as you can see, we offer services from the prototyping, supply chain management, and industrialization, but we can also integrate test systems into the production line. And we are working in a broad range of different markets, starting from medical, industry, automation, semiconductor, and also data telecommunication, where we see a growing demand for these kind of applications into semicon fiber, and recently also started aerospace products. Thank you.
So thank you, Andreas, for this interesting introduction. We move to Music Kim. He's going to talk a little bit about axetris. So Music, the floor is yours.
Hello, everyone. Antonio, can I share with my screen? Because maybe then I need to ask you clicking a lot of buttons. So maybe I will share.
Okay, you can share.
Yes, it will be the same slide, but just wait a second. Do you see the screen?
Yeah, we see. Thank you.
Okay, thank you. Thank you, Antonio, for the introduction. So axetris is leading manufacturer of micro-optics, including micro lenses, lens arrays, and also cylindrical lens arrays, and also diffractive optical elements. Our micro-optics products can enable many kinds of the optical transceivers. Some examples are shown here. If you look at inside, there are transmitting and receiving sub-assemblies, so-called TOSA and LOSA. Let's see what it does inside, like a laser diode coupling the light with a micro-optic to the optical circuits and coupling to the fiber and receiving back. What I'm talking about this is these days, a lot of optical setups look like this, complex, highly populated. For instance, applications are FMCW LiDAR or quantum computing or quantum sensing. But those applications you cannot make industrial mass production. So what will be the solution, which is a PIC, photonic integrated circuit? This one, even we can produce as small as like a few millimeters of dimension. These are why we are here today, talk about our micro-optics really couple well to the optical circuits and optical transceivers. If you just place the optical circuit or PIC to this position, this can be miniaturized as good as optical transceivers in communication market. So today, I think the PIC assembly and testing and packaging, I think you could appreciate our micro-optics very well. But not only this thing I want to talk about. For the highly integration, for example, this on the right side, the PIC has a lot of channels. In order to higher integration, you will need a lot more features like a mechanical feature, for instance, glue stops, spacers, precise dicing, metallizations for soldering. All these additional features we can make in wafer-level. Wafer-level means we can scale up more than 1 million micro lens chips per month delivery to you. This is what we can do today for you. So that's all. Thank you.
Thank you, Minsik. Perhaps, Ivan, you can go back to our presentation. So our last sponsor is SUS MicroOptics. I don't see anybody from SUS in the room. So, well, I want to introduce you this company. They are a supplier of quality micro-optics components, and they are working in different markets like data and telecom, also sensing, of course, automotive markets, and semicon and medical. And I just want to finish saying thank you to all our sponsors for supporting these events. We see that this PIC packaging and this very interesting topic for everybody. So we are glad that you are here today with us. And just a final word before going back to Ivan. For everybody, just join as a panelist. You will receive an invitation. So be sure that you join as a panelist so you can make questions directly, participate in the chat, and participate in the later discussion with us. So thank you, Ivan. You can go with the first speaker, I think.
Yeah, thank you, Antonio, for introducing our sponsors today. And without further delay, I would like to invite Jeroen Duis, the Chief Commercial Officer from PHIX Photonics Packaging, to share with us what you have on your mind. Jeroen?
Yeah, especially since Peter was having a fire alarm, right? So I'm going first.
That's right. He's practicing his firefighting skills now.
Let's see. So you can see my screen?
Yeah, you're good to go.
Okay, good. So thank you very much. I would like to give a small update on like PIC packaging motivation trends and challenges that we are seeing. So I already mentioned briefly in the introduction that we are a spin-off actually from Lyonics International, so a silicon nitride foundry, and they noticed that there's a need to do the volume packaging and ramp it up. So we started our operations in 2018, but since then we have been growing as a completely independent PIC packaging foundry. So you have an idea then like where we are located in the packaging field. What we notice is that not everybody knows what PIC packaging is about. So I have a small animation here to illustrate what are the processing steps that we are required to execute before you have a photonic integrated circuit which is packaged in a device. And some of the steps that you're seeing here are like the die bonding, the polishing steps, the active alignment in 6 degrees of freedom. We need to do accurate epoxy dispense on like these small chips, especially when you look to indium phosphide chips that typically have an area of like a few hundred microns by a few hundred microns. You start to appreciate the scale of it, since here everything looks very big and easy to access, but in reality the chips can become very small depending on the application that they're serving. You can nicely see like one of the final steps where we're actually doing the hermetic sealing of a module and closing it off, doing the wire bonding, and then hermetic sealing to make a hermetic package. If you're looking then like the motivation behind packaging, well, there are certain areas that we need to improve and certain challenges that we need to overcome. And to just provide already like what we need to improve as a roadmap is the signal and power distribution, is the protection from the devices when you're looking mechanically, electrically, and hermetically. We have the optical performance, so the losses that might be like a very critical target, and we need to do thermal management. And depending on like which market you're in, you might be focusing on one product or one area harder than the other. And of course, what we need to overcome is when people are looking for a better optical performance, is like how can we maintain the cost or even lower the cost in the end. The same as when you're adding multiple components in a package. One of the things that you're going to increase as well is reduce is reliability. So you would like to increase the reliability even though the devices get more and more complex. And of course, with the higher frequencies, the electrical crosstalk and the losses are getting more and more critical throughout the complete design. So to provide some of the market drivers and to elaborate with some images of things we have been doing, let's see where we can play a role and what impact they have on each other. So let's first take the lower cost. So as we are a contract manufacturer, it means we like to assemble modules that are designed by our customers. However, we realize that a lot of our customers start with a photonic integrated circuit and don't think immediately out of the module. So off-the-shelf prototype packages are available, but for volume, a lot of customers, they would like to have a customized package that fulfills all of their requirements. And it becomes clear that someone needs to take the responsibility of the product design as well as the ownership of the product. And of course, we can support our customers along the journey, but in the end, it needs to be clear that the product responsibility is owned by the customers and not by companies that do the contract manufacturing. Using standardized options to start with, they make sure that the investment in volume scale-up tools, devices can be pushed forward until a specific product and market is getting more mature. And in the electronics industry, especially in the consumer market, it's clear that when you need to invest in expensive tooling like molds in order to reduce the part cost, in photonics, we're typically working with metallic hermetic housings, and the cost scaling of that is completely different. And it may lower the cost initially when you're starting, but when you're looking to the scale up, the scale down in terms of cost is not similar as it is in the electronics. And what we also see is when you do tape outs in 2 different fabs for multi-project wafer prototyping, we typically get 2 different chip formats. And therefore also when it comes to the packaging, we also require 2 different printed circuit boards and 2 different products to get them in. So lack of standardization between the foundries and the chip formats are already limiting us to reuse the designs from one foundry to another. To elaborate maybe on like these devices that are optimized for packaging in early design phases. Well, if we are seeing to volume production, we have some customers that are looking to consumer parts and using 20-channel spot size conversions, including polarization maintaining fiber array. We're not seeing that scaling towards consumer applications. So I think it needs to be clear, like when you're looking at it, have a look at it when you want to reduce the cost. What kind of interfaces do you really require? If you require a single channel polarization maintaining interface, don't design a full fiber array with all channels to be polarization maintaining. And of course, having some margin in the power budget in the end will help you to allow for some manufacturing tolerances. And especially more tolerant designs in volume markets are highly benefiting from this. When you look to markets like quantum, of course, this is a no-go area and customers are hoping for hero parts one time after the other. So improved manufacturing tolerances and new designs would overcome this challenge and push the loss limits. So for prototype packaging, we have our own characterization package standard. So these are flexible, easy to adapt packages which are configured as a Lego style package. And we have a full suite of chip dimensions and electrical pad configurations already available. And for the RF interfacing, the modules can be easily upgraded with a custom radio frequent interfacing board. And what you see here are two different designs. So one is the design that we started scraping off ourselves from scratch, and the right one with the blue base, that's one that we developed together within the PIXAPP consortium. So customers that are using standardized housings for volume packaging, the direction of their choice is highly dependent on the needs of what they have for the package. And in the end, if you want to qualify a product for a certain market, or if you're looking to validate your initial chips, to take them off the optical table and show them to investors of your potential customers. The advantage of these packages that are already tooled, we keep them on stock. So that means there's no minimum order quantity or upfront housing design cost to get started, which makes it really an easy way to do customized prototyping. In order to scale up production of our customers, we need to be able to reduce the operator impact on the product cost. And in order to perform this, we focus on batch level automation on our tool set, providing flexible scale up. And once volumes are high for a certain photonic integrated circuit, a dedicated production line can be established as it's already done for the datacom device manufacturing. So here you see two movies of examples where we do a hybrid integration of a laser diode and bottom a flip chip integration. Sorry. Next on the list, the integration. So we are trying to stretch the limits of hybrid integration, ranging from co-packaged optics, chiplets, hybrid integration, heterogeneous integration. And in the example here, you see a demonstrator we built on with multiple chip technologies like indium phosphide, silicon nitride, and polyboard, taking the advantages of each individual chip platform. And due to the high-end assembly processes, the light can travel from one chip through another without degrading the optical signal too much. So this has been done within the EU TerraWave project. And here you see another example showing the hybrid integration of silicon nitride in combination with silicon photonics with various DC and RF electrical interfaces. Again, to overcome the challenges on one platform and leverage another platform on its own strength. And as you can see here, this is again using the flexible prototyping technology that we have, but then with a custom printed circuit board applying the RF signals into the chips. Miniaturization. It's also good to know that it's not always about miniaturization. So on one side, yes, we're definitely focusing on that. But what we are seeing is where electronics is scaling with each node, providing smaller and more energy efficient devices. Photonics isn't always about making it smaller. As an example, I have here a giant quantum processor that we have been built within the Q-Mode project together with PHIX Quantum. Here you see a wafer-sized photonic integrated circuit in the middle of the printed circuit board, and it has more than 3,000 wire bonds interfaced with multiple printed circuit boards to allow for a dense interfacing. And underneath this module, there's a 3 kilowatt chip cooler attached to take out the heat that is being generated within the chip and to provide a thermal stable platform for the optics. Similar as the example before, it's in photonics, it may require more complex wire bonding schemes than the electronic counterparts to allow for standard printed circuit board technology. So the lack of serializers on the chip and the large number of IOs that are on die level need to be interfaced to the board. Staggered wire bonds are an approach to overcome this challenge, but they are not widely used yet in the industry. As we mentioned, photonics and electronics scale differently, but more than Moore's law is also applicable here as well. So in photonics, for example, we can co-integrate these lenses. In this case, it was 3D printed. I think as Mung Sik was just mentioning from axetris, you can also make them wafer scale and then you can flip chip them on. I think the big advantage here, in this case, when we do the printing of the lenses, we can reach accuracies with placement with respect to the grating coupler of about 100 nanometer. And this is a tolerance that cannot be obtained yet by flip chip assembly processes today. Next, the integration on the thin film ceramic board makes sure that the wire bond density on the photonics can be natively wire bonded to the dense thermally conductive interposer. And therefore, this design is helping to get more functionality per cubic millimeter instead of focusing on the square millimeters of the chip design itself. Modules go up to higher frequencies, and where on one side we are discussing with customers that declare 100 megahertz as RF, on the other side we are stretching the requirements to a staggering 120 gigahertz. And we have simulation tools like ADS and ribbon wire bonding, stretching these requirements on the design and manufacturing side. And then looking to robustness, of course, before a product is being accepted for a certain market, thorough tests might be executed to reveal the weak points within a design. So test plans for integrated photonics, they're still pretty limited. And quite often it's telecommunications and telcordia requirements used in the initially reliability start. However, one needs to check the applicability for telecom and laser, since in telecom, a laser needs to function 24/7 for a period of 25 years, whereas in automotive, it only needs to last for 10,000 hours in operation over a period of 15 years. And most of the time, your device is actually in an off state. So therefore, to conclude the presentation, I have some key takeaways. So we help our customers in an early stage with packaging roadmap for their products to help them out from a prototype to a qualified product. So don't look only to your device you want to have next, but more like where you want to be in the end and draft down the whole roadmap from there in packaging. And that may help you as well to secure enough funding and not be surprised in between of the expenses that you're running into. Of course, we try to reuse as much as possible from existing designs to limit the scale-up cost and to mitigate design risks. And we work on new processes to further stretch the integration possibilities. What's not yet available today may become available as an option for you in the near future. But when you require product tomorrow, please then start by using a known process. So the number of risks that you're stacking into a product when you launch it, you would like to limit that as much as possible. Think of how your product scales. What do you require and what components do you require to scale up with a lower cost? And polarization maintaining fibers, as I can see today, they remain rather expensive, even though the volume requirements will go up quite a bit in the future. Photonics does have similarities and difference with respect to electronics. And I think we just need to be aware of them since they may work advantages or disadvantages for your product. With this, I would like to conclude my presentation. I'm open for any questions. Thank you.
Thank you very much, Jeroen. That was a great opening presentation. And yes, I would like to remind you that you can we have a possibility to ask questions to all our speakers. Just use the raise hand button at the bottom of your screen. And do we have any questions in the audience? In fact, Jeroen, it was you showed us a large variety of packages from the ones we're used to all the way up to the wafer scale packages. I'm wondering, what is the trend that you see for photonic packaging? The variety of different packages keeps growing, or are we going towards a standardization?
I think what we are seeing clearly is that the variety for certain packages is decreasing. So I think telecom and datacom, since they're using photonic integrated circuits for a longer time, you see a stronger converge. I think when I look to other markets like LiDAR, quantum, medical, I see them diverging even more and more since they have completely different needs. So for quantum, people are very happy to pay a few euros more as long as you're focusing on the optimal performance that you can get out of a device. Whereas for medical, you're looking to consumable parts and it needs to be as low cost as possible. And it doesn't need, it now does need to be reproducible, but it doesn't need to last typically for like tens of years. We are working on quite some of these applications that require consumable parts. So they need to work out of the package, you use them once, and then you discard them. So they have completely different requirements when it comes to packaging and scale up.
Right. So strongly depends on the application.
Yeah.
All right. We have a question from the audience from Carol from Photon Delta.
Hi, Jochen. Nice,
Hi,
nice overview. I like it. On your last slide, you showed an intriguing picture of an epoxy package, which so far has been, as far as I know, at least fairly limited in this industry. Is that something that you see progressing, or is it still rather experimental?
Well, what we are seeing is hermetic packages are the de facto standard within the telecom industry because of the long lifetime that they can withstand. But other markets may be open for new approaches. So if you're looking to automotive, and also depending on which chip platform you're using LCP or polymer packages might be like a much better way to scale up to reduce the cost. If you're sticking to the materials we had so far, so we are not changing the bill of materials, then the cost will not scale in the volume. So having injection molding solutions, that would definitely help. And we need to work with our customers to figure out, can we use semi-hermetic packages for a lot of applications, and is that good enough?
Thanks.
All right, and Marco from HNS. Please go ahead.
Hi, Jeroen.
Hi, Marco.
I have a question regarding the supply chain. So I agree with you, these processes are so special that is a perfect way to start and as a niche into the market. When this is combined with the when co-packaged optic comes, there are also conventional flip chip assemblies. So flip chip on substrate, SMT mounting, and so on. Yeah, how these two will somehow play together? Yeah, will PHIX support both? So flip chip, SMT, and the final module basically, or do you see in the future also that photonics might remain the niche where is to play, and then the rest will be done by OSATs like ASC, Amkor, or JSAT, whoever it is?
Yeah, I think there's multiple ways in there. So we play a role. So we have flip chip equipment, and we do a lot of first level packaging. So for example, a chip to an interposer, so that you have a redistribution layer that can go to a standard BGA approach. And customers like that we can do like a fiber attach. So basically then you have a BGA with fiber pre-attached, and then a existing OSAT can take this as a module and solder it or integrate it into the complete system. So I think people are trying to figure out like, where are we going to do what to build a complete device. When it comes to chiplet stacking, so we also do a lot of stacking of like electronics directly on top of photonics, and then like on a redistribution layer BGA package. So it's really like getting the different functionalities in the first level package.
I understand now. Thank you.
Yeah, welcome.
Ivan, Wilfred from SUS MicroOptics also have a question for Jeroen. So Wilfred, you can proceed.
Do you need to unmute?
I
maybe?
think you're muted. You're muted.
Can you hear me now? Sorry.
Yeah.
Now it's okay.
Okay. I thank you, Jeroen, for that very broad presentation. So you showed the 3D printed lenses earlier.
Yeah.
What is your experience with 3D printed lenses? Because we know that they're not yet the equivalent of micro-manufactured, micro-etched, micro-fabricated lenses by etching or by imprint. So this is our experience from 3D printed lenses. Do they give you sufficient good performance that you can have a representative setup for your clients then, or?
So I think what we are seeing with the 3D printed lenses, the biggest advantage is you can play with different optical designs throughout your journey. So what we are seeing is like a multi-project wafer run, depending on where you're getting it from, may have some differences even across the chips that you're getting. So having 3D printing as a option is then really helpful for the prototyping, at least, to find your optimal lens configuration. When it goes to volume production, we are not seeing that this 3D printing will play like a big role. The only thing where it will be very important for is making the masters that can then be replicated actually for wafer level imprinting, so that you're using basically a nano imprint lithography setup to replicate it over the complete wafer.
Okay, and the quality you've seen so far, is that sufficient for coupling, or?
Optically, the quality that we are seeing is really staggering. So we have lenses that we are delivering printed on fiber arrays. So either for collimation or for parallel optics to do testing of photonic integrated circuits. And that works out very nice also for wafer level testing. And on the other side, we do printing, for example, on top of silicon photonics to get a collimated bundle out of a silicon photonics chip, which is also working very well if you're looking to the quality of the lenses, but especially also to the high through positioning you're getting with respect to the grating.
Okay, yes. Thank you. Good to
All
know.
right.
Thank you.
Thank you. Just the very last question from Untitled Axetris.
Hi, Jeroen. Thank you for mentioning about wafer-level micro-optics from us, probably as well as SUS. But I have an additional question regarding to this 3D printed optics. How about reliability? You mentioned as well tachydia test. Usually polymer optics is not recommended tachydia testing schemes. So how is your experience with that?
So I think for a multi-project wafer packaging, it's really about prototyping, first validating the performance of your chip and testing that. So that's where we see that these lenses are being utilized a lot right now. Second step is when you integrate it into a product. And I think for a product, when it's fully hermetic, these lenses can be utilized as well. I think the biggest barrier is typically the moisture or the energy density. And those are kind of tests that we're actually executing also today to figure out like, well, what is the reliability level that these lenses have in a protected, but as well in a unprotected environment.
Thank you. I agree about the packages. Yes. Thank you.
All right. We'll start with a very intense discussion today. Thank you again, Jeroen. And let's pass to the second speaker, who actually was supposed to be the first speaker today. So Peter O'Brien, the head of research group in the Tyndall Institute and the director of the Photonic packaging pilot line PIXAPP. Peter, please, the floor is yours. You might need to.
So can you see my screen? I'm going to share it.
Yes.
Perfect. Okay. Thanks, everybody. Nice to see you all again today. Apologies about the confusion. We had a fire alarm, so we had to evacuate the building, but fortunately, it's all okay. So very interesting talk from PHIX, and PHIX are a partner in our pilot line, and I'm going to talk a little bit about our pilot line, but more around the area of technology sustainability. So one of the key kind of requirements or activities in the pilot line funded by the European Commission a number of years ago is that we're sustainable financially, but also technologically. And I think this is really important because there was a question about the future. So where we see packaging going is it's still very much in change. And, you know, looking at a lot of the packaging, it's done part by part, what we call package level. And really where we want to go to is wafer level, much like what's done in the microelectronics world. So developing a sustainable technological approach in the future is very, very important. It's not fully there yet, but we are working on it. And I just want to talk about what we're doing within our pilot line and related projects to enable that. So just very, very quickly, you may have seen these slides before. So PIXAPP is a distributed pilot line. We have multiple partners across Europe continuously growing. And one of those important industrial scale-up partners is PHIX, who have kind of been with us from the start and grown and increased their capacity and technological capabilities. And Jeroen mentioned about some of the pilots or the prototype packages. We worked together to develop those. So when you want to look at evaluating devices at an early stage, rather than investing in tooling in very expensive packages, you can use the PIXAPP fairly standard prototype packages. We have a range of technologies, very, very straightforward. And as I say, the way it's organized is we have a development kind of service activity primarily located here at Tyndall, where we look at engagement with users. We give training, very important. And we also do the high-risk development and early-stage prototyping. And then with our industrial partners like PHIX and others like Ergotech as well, and we have a few companies in that space, we transfer projects or scale-up processes with them. We also provide those companies with access to equipment that we might have that they may not have available. For example, Ficontec are now located with us here at Tyndall. So they have pretty advanced machines and we can work to optimize machines or give access to our industrial partners, you know, test before they invest so they can make a good choice of equipment. And that's very, very important. A very important part, and I think the key part of what we've done over the years in PIXAPP is developed up standards. They're not formal standards, but really around design rules. And that's so important because quite often, and we still see people coming with chips that we've had no hand or part in designing, at least giving advice. So how you lay out your optical, electrical, and very important in RF. So it was mentioned the previous speaker around RF packaging. So it's very, very important to be able to configure devices. So this is a 3D stacking of IC, driver IC on a silicon photonic chip with DC and RF interfaces. And we have design rules around that, and we're expanding and bringing those to not just photonics, but also co-packaging with electronics and even MEMS integration as well for things like LiDAR, time of flight, and so forth. So the design rules are a key part of what we're doing. But moving forward, as I say, much of packaging is done part by part. So even with gold boxes. So if you want to scale up your process, you basically either pass more devices through your machine and you try and kind of shave off time to reduce the processing time, or else you just buy more machines. And, you know, with the volumes that we're beginning to see, hundreds, thousands, tens of thousands, even millions of parts scaling rapidly, that's a real challenge. It's actually a big problem. So we need to move more to wafer level. So I feel like we can learn a lot from the MEMS industry. So what you see on the right-hand side is pretty much a MEMS type package, but kind of adopting a similar approach where much of the packaging is done at the wafer level, even hermetic sealing is done at the wafer level, and then you get optical access, you know, by certain means. And I think somewhat bonding fibers to packages to chips is not viable because it's really based on a package level approach. So how do we get around that and how do we move forward to this more wafer level kind of assembly? So what you see on the left-hand side is a pretty standard approach. And we've been talking about this for some time on the right, where we're integrating micro lenses onto the chip. Now, in this case, you see a micro lens onto the edge of the chip, and then collimating, expanding the beam and refocusing it into a fiber array. And actually, that fiber array doesn't have to be an expensive glass fiber block. It can actually be molded. So you can make a molded micro lens array with receptacles for ribbon fiber, and you know, essentially make a very low cost type solution. Now, this is still at chip level, so because the device has to be singulated. But I'll get onto that in a second, where we're moving towards and what we're looking at doing in one or two of our kind of ancillary projects related to PIXAPP. So where we're bringing in these new technologies, hopefully to scale them up. So historically, we've been working before where we're using grating couplers, and grating couplers are fantastic, although there's limits to what they can be used for. So you can see we made these homemade connectors, and we connected, a pluggable chip with this fiber array. Now, it's not a molded part, it's a glass fiber block with micro lenses, but again, you can see the principle. We're kind of separating the fiber from the actual package. So we're kind of moving more to kind of chip or even wafer level. Just to show you where that kind of technology does have an immediate fit. So this is a biosensor, so using evanescent sensing. And this is work we've done with some partners, AEMtec and University of Ghent, Roel Batz's group, where we looked at biosensing on a silicon nitride platform. And again, you can see the principle of the expanded beam into the micro lens array and detection. So basically evanescent sensing and using photodetectors on chip, and you can see the electrical pogo pins, which basically sense the electrical signal. But the idea here is that this is a disposable chip, so you can pick it up, put it in, and because the beam is expanded, you got fairly relaxed alignment tolerances. So again, you're using the expanded beam. So it shows you a nice application, immediate application for that expanded beam approach, where you're not bonding the fibers or putting a laser on the biosensor, which is disposable ultimately. It's also important to mention we do have a design kit around that. So there is a design rule. So everything we do is around design rules. Just to show you again, the principles here, you can see the micro lens with the chip and the fluidics. And I won't dwell on this too much, but that actually works quite well. And we have with some of our industrial partners like Ergotech developed a scalable process. So it reduces the barrier for companies to be able to, invest in early stage kind of prototypes to look at, see if microfluidics and integrated photonics can be used to replace other types of sensing kind of modes. But I showed earlier around using grating couplers. So moving on then to something a bit more kind of relevant, a bit more up to date, let's call it edge coupling with large mode sizes. What we've done in our pilot line, because one of the big challenges we see is getting access to sufficient numbers of chips. So you may have heard me mention before around reference chips, and these are basically very simple optical or electrical kind of chips with different types of loopbacks, etc., a whole array of packaging structures. In this case, it's just simple optical IOs, but we make lots of them. We made a large number of wafers and made thousands of chips, and essentially just use them for packaging tests. So for example, companies like Ficontec can use them then for machine installs. We don't need to use valuable product chips. So these have proved very, very successful. And in this case, we've used these chips. These are Line-X-based chips with a 10 micron, the triplex platform, 10 micron mode adapter. And using chips from SUS off the shelf, we wanted to demonstrate this pluggable type connector. So you can see some component details here. And what we've done in this case is put the micro lens at the edge of the chip, expand the beam, and again use this homemade connector part. So you can see the fiber. This is actually where we're aligning the chip. So we're aligning the actual micro lens to the edge of the chip with the loop back. So light in, measure the light out, and maximize the coupling efficiency. And we've demonstrated that, and you can see here a working demonstrator. You can see the coupling efficiencies. So when we apply the epoxy, by the way, these chips are diced, they're not polished. Because of the index, when we apply the epoxy, we get pretty good coupling efficiencies. So you can start to see now we're moving away from bonding the chip to the facet, bonding the fiber array directly to the facet, making a pluggable connector. What's also interesting here is that the connector here is not the actual, in this demonstrator here, it's not the glass block. It's actually a molded part. It's a molded micro lens array in a connector. So you can start to see that the price or the cost of this type of module can be driven down. So I mentioned earlier about design rules. So one of the challenges in this particular case is aligning the micro lens. So you need a fiber input the light and collect the light back out and align the actual micro lens onto the chip. What we've done here now, we've introduced a new design rule. So these alignment waveguides, by illuminating from the packaging machine itself, you can align the fiber using these active waveguides here. So we can just illuminate and see where the beam is collimated. And then all the active waveguides in between are aligned. Basically, it's just self-aligning the active waveguides. And we developed some chips around that. So you can see we haven't put the light source on the machine itself, but we're using, these are just red to pilot illumination lights. But essentially all you need to do is spot illuminate the grading couplers. So you can see the grading couplers here. We can quickly find those to edge and then align the actual intermediate loopback waveguides for testing. So you can see this kind of simple design rule enables the actual micro lens to be quite simply packaged to the edge of the chip. But as I said earlier, we're trying to move to wafer level. So what we're looking at now in a project called Photonic Leap, so one of our partners, SUS MicroOptics, we're looking at out-of-plane coupling. So using microprisms to couple out of plane and then use the micro lens to collimate the beam. So we're just starting on this process, but you can see these components, for example, have been developed by Wilfred and the team at SUS. So using integrating the actual microprisms, so out of plane coupling with the micro lens on the opposite side of the actual chip, can collimate the beam. The beautiful thing here is that it enables 2D coupling. You don't need epoxies anymore. You can do solder attach, so replace solders. Also, it's on the surface, so it's much easier from an alignment and a machine vision point of view. So that's kind of where we're working towards. On top of that, Photonic Leap is also looking at the electrical package. And it was interesting to see the low-cost type of molded lead frame, because we're thinking along the same lines. So moving away from the gold box, looking at surface mount type packages, which are very low cost and standard in the electronics world. In this case, we're using glass as the interposer base and also using true vias, so filled copper vias, both for electrical contacting, but also thermal vias. So you can see the concept here, where we're using the BGA platform for electrical powering at the bottom and optical outputs. So again, using that type of out-of-plane coupling approach. So we're about over a year into the project and we're starting to develop these with some of our partners in glass. You can see the true vias, the RDL, the redistribution layers, the MicroOptics, integrating lasers, etc. This will be done at wafer level. So the big advantage here then is one of the things we're really trying to get towards is be able to do multi-project packaging runs. So enabling companies to cost share at an early stage and then to increase the volume as they need to go forward. It also enables wafer level testing as well. So this is important because it enables us to look at new technologies moving away from the package level approach to more wafer scalable approach. And that's very important for future pilot scale packaging. So I'll leave it at that and open it to questions. Thanks.
Thank you. Thank you very much, Peter, for the very inspiring talk. I'm sure there will be many questions now. This is the audience. This is your chance. And Jeroen, go ahead.
Peter, thanks for this excellent overview of where we can go in the future with wafer level packaging. I was actually wondering, when you're looking to these interposers, what kind of resistances are you getting with these vias? Because I think like when you're looking to printed circuit boards or like lead frames, the resistances are pretty low, but I think for vias, it can be quite different, is it?
Well, that's a good point, because actually what we're trying to do here is two things. So we're looking at the thermal as well as the electrical. Many vias are normally just, how could I put it? They're not filled vias. Mm-hmm. They're coated around the kind of perimeter of, or the kind of the inside or the outside of the via. So just the wall of the via. What we're doing here is filling the via. So it'll drop the resistance significantly and also drop the thermal resistance. So generally what we're looking at is vias around, say, 50 micron diameter, and we're working around changing the pitch. So yeah, it's a very valid point. So filling the vias with copper is where we're going to reduce the resistance both electrically and thermally.
Thank you.
Now Ahmed from CMC.
Yeah, thanks, Peter, for the presentation. I want to ask about, you talked about, the wafer level packaging for the, the microprism and then the lens. How is that done in a wafer level? Like, because I'm guessing like you need to align first the prism and then place the.
There's two approaches.
Standard.
There's two approaches where you actually have an independent or separate microprism. So you basically drop the microprism into a shallow, it's not a fully etched. So for example, many foundries now etch the facet. They etch them maybe to 100 microns, and then they have this ledge, they dice. So the process is already in existence. You can etch the facet, but you're not etching a full facet, you're etching essentially a small pocket around the waveguide. The prisms typically are in the order of, say, 50 microns. That's typically. So that can be done at wafer level. You basically, for example, you can print the prism. You can pick and place these in, and then separately placing micro lenses on top of that. What we've been working with SUS on is integrating all of those, the prism and the micro lens, in a single unit. So these can be pick and placed and dropped into these smaller pockets.
Oh, okay, interesting. Okay, thanks.
Yeah,
okay.
and as I say, because it's at a surface level, it's possible to use a solder, gold tin. So you're bonding the base of the micro lens prism assembly to the top of the silicon, for example, and you can use laser-assisted reflow.
Okay,
so that's generally the approach, so eliminating epoxy.
Okay, so what's the tolerance, like the placement tolerance of
those? Well, the requirements are on the similar to bonding a fiber. So it needs to be plus or minus a micron or so. That kind of, or even better. But that can be done. Pick and place at that level is not really a challenge. And it's easier because it's on the surface, not on the edge.
Mm-hmm. I agree. Yeah. Okay. Thanks, Peter. Thanks.
Yeah, that does sound like an interesting approach. The next question is from Amir from CSEM.
Peter, this is as usual a very nice talk, and I always enjoy it. Actually, sort of for this vision of wafer scale. So do you think that sort of for edge coupling, edged facets are enough, or how to get away from polishing at that wafer scale?
Well, the etch is usually doesn't need to be polished. There are other approaches like membrane couplers. And Global Foundries have a membrane coupler. I think AMF have a similar type of membrane coupler. There's different approaches. Actually, that's one of the challenges we face, because I'm sure PHIX see the same challenge. There's lots of different couplers. There's lots of different dimensions. There's different mode sizes. So there's lots of choices. And I think we need to kind of maybe start to reduce those and consolidate the number of designs. So, as I say, you don't need to polish. You don't always need to polish.
So you think the edge facet would be enough to give sort of a reliable and repeatable? Okay. Fair enough.
All right. Next question, Tobias from Genoptics, please.
Yeah, thank you. My question would be, so Peter, you mentioned that with these prism and a lens approach, you could enable wafer level testing of edge coupling devices. So, but that would require that you would need to assemble the complete wafer before wafer level testing, or would you require a wafer level test before to save some parts or
no, the beautiful thing here is that you do all the essentially the key packaging before the testing.
Mm-hmm.
Yeah.
So also when it is die by die assembly.
You can do it die by die, but you can still do it on wafer level, because if you put the optics on at wafer level, you can now have optical access. You basically just need a collimated light source to basically collimate the beam, much like the connector plug. So you scan across the surface.
Okay, thanks.
I will just take one last question from Frank. Focuslight Technologies, please.
Thanks, Peter. I wonder, is it possible to assemble using the crossed cylindrical FAC array?
The which?
If you have FAC on one side, another side with SAC array, so it's a crossed structure. Is it possible to achieve the assembling by this kind of structure?
Sorry, I'm finding it hard to visualize exactly what you're asking.
It's also kind of micro lens array, but on one side is the FAC, it's a cylindrical structure. Another side is just like a SAC array, so it's crossed. I don't know if you get it.
Okay, so you're talking about correcting for astigmatism, is it, with two cylindrical lenses crossed?
Yes. Yes, yes, but it's a monolithic to one structure.
Yeah, possibly, but you normally you possibly could. One of the challenges, and Wilfred knows all about this, you need an epoxy on potentially on one side. So if you need epoxy to bond, the cylindrical lens main approach may not work, but you can put epoxy dots, for example, on outside the active optical area. Then you could use cylindrical lenses. Yes.
Okay. Thanks.
All right. Thanks to everyone. I think we can continue this conversation for much longer, but please stay with us after the end of the event. We have time to discuss longer. Thanks again, Peter. And with that, I would like to pass to the next speaker of today, Jochen Zimmer, sales manager from Nanoscribe.
Okay,
Jochen,
thank you.
Hello.
Can you see my screen?
Yes, you're good to go.
Very good, thank you. So yeah, let's dive right into it. I'm talking at a little bit, let's say, lower height of flight. We are a machine manufacturer, and we build 3D microfabrication systems, such as the Quantum X Align system that you can see here on the left. Our systems are 3D printers for polymer microlenses that have been discussed already a couple of times today. And so we use 2-photon polymerization as opposed to conventional UV polymerization or lithography. We use a femtosecond near-infrared laser, and this gives us a high degree of control over the position and the size of the polymerization that takes place. Our systems use the laser source and then a couple of galvo mirrors for beam positioning, and then we go through a microscope objective that focuses the laser light into the sample volume where the 3D printing takes place. In case of the Quantum X Align, we have two sensor systems that allow us accurate accurate detection of features like markers and automatic alignment to that. So this allows the printing of polymer micro-optics, for example, among other structures. And here we have years of process development experience, which allows us to print lenses with reliable, repeatable, high-quality optical surfaces, as well as finding a compromise in terms of printing speed. So some surfaces that are not optically active may have a reduced quality. With this, you can print directly onto photonic chips at the chip or wafer level in principle. And in such a situation, we use the confocal module, so one of the detection mechanisms here, which looks at the back reflected light through the beam path. And this allows us to get a 3D position detection of features on the photonic chip. For example, alignment markers from previous process steps, or chip edges, waveguide, corners, things like that. And now with the exact knowledge of the position and the angle of the chip, you can print coupling structures, microlenses, for example, aligned in position and angle to the chip. So just one quick example here would be these lenses that were printed onto an edge emitting set of light here. These are waveguides. This could be lasers or light sources or something like that. And as you can see here, down in this comparison between the simulation and the measurement. So here's the lens, and we look at the light intensity, and you can see there's an excellent match between the simulation and the measurement, meaning that we have understood and can predict and can create the right beam profile as requested. You can also print on fiber, so single fibers or fiber arrays. And so in that case, the setup would be looking something like this, for example, with a fiber in a V-groove holder in an array. And here we don't have alignment markers. So instead of the confocal module, we use a camera system and fiber core illumination from the other side of the fiber to allow automatic detection of the fiber core. And we can also look at the emission direction to also align to the emission direction of the fiber. And in such a situation, again, just one example, you would automatically align to and print on all of the cores in such a fiber array. And again, we show that we have a good match between the simulated beam path and the measured beam profile. Lensed fiber arrays like these are available through our partner PHIX, who also spoke earlier in this session. So if you just contact them or go to their web shop, you can get a set of fiber arrays printed with lenses with our technology on that. So just briefly, we characterized these, and there are two typical situations that get asked from us by our customers. So either you have either a fiber or a waveguide with a printed lens where you want to collimate the beam to a relatively wide beam diameter, or you want to focus to a pretty small spot. This has already been discussed previously, also, that with a wider beam and a second set of micro lenses, you can get relaxed alignment tolerances. Or if you just want to have a single lens and no second lens on the other side, you could use the fiber to directly match the mode field of the target waveguide. We characterized both these setups. So up here we have two fiber arrays with lenses printed on them, and we are testing coupling through 1.2 millimeters of free space. In this case, we designed for and tested with a green light 532 nanometers, sorry. And here we see indeed relaxed alignment tolerance. So we have plus minus 5 micron alignment tolerance for 1 dB of axis loss. And we found 0.7 dB loss per lens. So two lenses in the beam path, 0.3 of which per lens are just from Fresnel losses, which could in principle be mitigated. Down here, we tested this other scenario with a lensed fiber array directly coupling to a silicon and insulator situation. And here we designed for and tested with 1550 nanometers, and we found losses of 1.7 dB per coupling interface for this test. One last slide, we talked about wafer level testing. And of course, if you can build your setup that you already have out of plane coupling, then you're good to go for the wafer level. If you have edge emitting or generally edge coupling chips, then you need to somehow be able to look around the corner if you want to do it on wafer level. And for this, it would be possible to get such a fiber array with periscopic lenses printed on them, and then to use that for wafer level testing, like our customers here have done and published 2 years ago, Optics Express, where you have here basically your fiber array, and then these periscopes can be dipped into these edged grooves on the wafer to look into these waveguides from the side. That's all. I hope there's time for a few questions. Thank you very much.
Thank you, Jochen. Yes, this is the time for questions. Ahmed from CMC. Go ahead.
Thanks for the overview. I want to ask about, the optical return loss, of these lenses. Another thing is the high power capability, and also the scalability, right? Do you align and then you do this process quick? How fast, for example, if you do a fiber array, how quick you can make?
Yeah, so with the whole process, the automatic alignment per fiber, and then the printing process, we're looking at a couple of minutes per lens. So typical lenses that look in the same direction as the fiber would be 2 or 3 minutes per lens. And for the periscopes, because they have more optical surfaces, they need to take a little longer. There it's more 6 to 9 minutes. So this is not currently a large scale process, but it can be used for small scale production and especially for prototyping.
Okay, thanks. How about the return loss? Do you have any number about that you tested for?
I mean, the losses we mentioned here basically. So we have here 0.7 dB total loss of the light going through the lens. Okay. And some of it is reflection, some of it is just in transmission. So the total loss is 0.7 dB So I don't know the number by heart. We have a couple of tests for a few wavelengths of the power. Please contact me afterwards so I can give you an exact number.
Okay, great. Thanks.
All right, thanks. If there is no other question, I'd like to pass to the next speaker. Thank you, Jochen.
Thank you.
The next speaker of the session is Jean-Luc Polleux, the CTO and the co-founder of Icon Photonics, Paris. Jean-Luc, whenever you're ready. Please unmute. Jean-Luc, you need to unmute. Jean-Luc, still cannot hear
Yes,
you.
thank you. Can you hear me now?
You're good to go.
Okay, thank you. So thanks for letting me giving this presentation. So I'm going to tell you about Icon Photonics and our technology, which is made in polymer to enable the packaging of integrated photonic circuits and for the next generation of optical connectivity. So, well, actually, the context, actually, we have already browsed in this webinar, but I would like to insist on the fact that there is a great reduction of dimensions nowadays that we are looking for. And actually, if you are looking for pluggable optics, you go to co-packaged optics and then soon to 3D chiplet. And as was said, actually, there is also another trend, which is to go to lower dimension to get higher speed and higher density, but also to go to the wafer level in order to enable mass production capabilities. That's what we are working on, and actually I can give also two examples on the subject that we are considering. First, the datacom, where you are targeting very high data rates with today 112, 224 gigabits per second, and you are running toward higher data rates. So sure, you can do it in parallel, but also per channel you want to increase your data rate, and in this progress, the packaging is getting more complex, and you need to simplify it and to reduce the cost, but also to enable higher performance. When you look at the second example, which is looking for the quantum supremacy, there is another challenge. There you're trying to have a higher number of qubits, which is a fundamental element of this quantum computer. And today you have up to 433 qubits. What is the challenge there is that each qubit, for example, is a photodetector, which is a supraconductor photodetector cooled down at cryogenic temperature. And the packaging of each individual detectors is almost macroscopic packaging. So if you really want to go to larger number of qubits, and if you want to have a useful quantum computer, you need that. You need to target more than 1,000 qubit. So you really need to shrink down your packaging for that, and to be also compatible with very low temperature down to the milli-K. So that's what we are tackling with our solution, which is an all-in-one package, actually driving the photonics, the electronics, and the mechanical integration at wafer level. So we start actually from the device of the client, either as a wafer or as a chip, and we assemble them with these structures that we are providing, either with surface alignment, and there you will see in detail a polymer structure, which is shown there, which is providing the low loss coupling with a taper shape, which is showing a large area at the input and a small area at the output where you have your detector. So it's concentrating the beam. The large array helps to relax the tolerance of alignment of the fiber. And then with mechanical structure, which is fixing the fiber on top of it, you can really have a first mechanical alignment, then you finish the work with this optical focusing of the light on the taper. This solution, which is shown here in surface coupling, is also used for the edge coupling of a ribbon fiber to a PIC, to the edge of the PIC. If we go in further detail for one example of this structure, you can see here the different parts which are separated. First, you have a silicon interposer in which you can put the chip, and then you can have electrical interconnections up to millimeter wave. Then you have the polymer taper and the fiber holder, which is on top of it, and then you have the fiber. Here is it when it is assembled. So you can see, for example, that the fiber holder is very small, and in that example, you have 12 fiber which are coupled into this fiber holder. This is a kind of advanced V-groove. So you really align precisely the different fibers, and at the same time, you fix it firmly so that when you go down to cryogeny, you don't have any movement in any directions. The polymer tapers, you can see here different geometries, which are more compact or taller, depending on the geometry that you are targeting. And for example, here you see the fiber holder, the taper, and the chip, which are bonded all together. And that is a wafer level process, except the fiber insertion, obviously, which still is individual, but can be automatized. So finally, our solutions, we have surface coupling, edge coupling, and surface to edge also, which is upcoming soon. And for the surface coupling, these are the kind of geometry you can have from an optical aperture, which is 70 micron down to 10 micron with MMF fiber, multimode fiber. And then we can enable 0.1 dB coupling losses. And the same for single mode fiber or multi-core fiber, because by sense, this technology is wafer level, so you can make an array which is a two-dimensional array. In the edge coupling, the coupling loss are low again, below 0.5 dB, and that is a very good progress compared to state of the art. And we provide two solutions: a standalone option where you align actively the chip to the PIC, the fiber holder to the PIC, or even a passive alignment where we have mechanical clipping options to provide. The polymer that we are using, I was also listening to one of the questions, which is about reliability, is quite robust polymer. And then we can also have some process on top of it, like a zero air gap option that we can provide, and to reflect coating, and the polymer is really reliable. So it goes from milli-K to very high temperature in excess of 350 degrees Celsius. And we also have, obviously, this damp heat test, cycling test, and that makes the lifetime of the device very acceptable. So our collaboration model, actually, we're providing design and test for the client, fast prototyping as well, so that we can develop the proper solution on top of the chip of the client and provide small series sampling. But we can also obviously go to fabrication and production from low to medium volume and even high volume. And that is really the idea of the wafer level process that we're using. So this is the end, just to keep in time with the 6 minutes given. And the final question that you are asking, what we can do for you. Well, we can bring to packagers standalone options to ease the coupling. So in that way, we are very compatible and complementary to the approaches. So we can provide better performance for you and ease in difficult conditions, or easing simply the standard one solutions. But we can also bring to module makers higher performance and yield for their production, and from cryogenic room temperature to high temperature. And finally, we make it smaller, but denser and better. That's what we can do for you. what we are looking for, obviously new challenges, just like the quantum computers, trying to tackle the more than 1K qubits or even 10K qubits, tackling higher data rates when you need photodetectors to be smaller, for example, and then we can really help you to shrink down the dimensions. Today, we already have early stage adopters, so we want to expand, obviously, and to be and we are ready to cooperate with new clients and exploiting also our mass volume capabilities.
All right, thank you, Jean-Luc, and thanks for answering clearly to the EPIC question right away. It is now open for more questions from the audience. In fact, I was wondering myself, what is the current cycle time of your process on a chip? And what is the forecasted cycle time when you go to high volume manufacturing?
Right. Actually, going to the prototyping to volume production is quite easy. Actually, the idea is really because we're wafer level, adapting the process on top of your wafer, and depends obviously of your surface state, of the different materials you have, and so on. So the longest part is clearly the prototyping phase, because we need to have a common work together, and it's a question of weeks and months, we say a few months to make it, which is a typical clean room cycle. Not so much more, but a typical clean room process development.
All right. Another question from Ahmed from CMC Microsystems.
Yeah, thanks, Jean-Luc. Just to confirm, like you showed in your slide that you have, a better coupling with the vertical coupling scheme than the edge coupler, right? It was, I think, 0.1 and the edge coupler was 0.5 dB.
Right.
Okay, because I was guessing like if you have a grating coupler, right, there will be some mode conversion loss, right?
Right. In the case of grating coupler, actually, you can still challenge this 0.5 dB. On the edge, actually, here you don't have a grating coupler. This value for the top side, 0.1 dB, is without a grating coupler. It's clearly directly to a photodetector, and the grating coupler you will be similar to 0.5 dB.
Mm-hmm.
There is also an advantage with our technology with grating coupler, is that the grating coupler, you need to give an angle to the beam, to the fiber to couple to it, and actually we will help to make it vertical again. So you don't have to bother on the fiber placement with an angle to put it on it, and the taper will manage it for you. And that has an advantage, because when you change the temperature, for example, and you have your laser on board of your PIC, the wavelength is changing, and when the wavelength changes, the angle of emission out of the Bragg couplers is also changing. So when you go to vertical emission again, then you are enlarging the bandwidth range of your grating coupler.
Mm-hmm. Right. So this is not the grating coupler; it's directly to the photodetector, right?
The 0.1 is directly to a photodetector, and grating coupler is a 0.5 dB.
Okay, great. Okay, thanks.
If there is any other question, and if not, thanks again, Jean-Luc. And I'd like to pass the word to, well, okay, let's take the last question from Amir, CSEM.
Yeah, Jean-Luc, this is a great talk. I mean, so I see a lot of investments since the last time we met. This, so values 0.5, I mean, these are inferred, actually measure them, because, 0.5 to a single mode, it's really, really, really difficult, actually.
It is indeed, but that is real values, right?
So you measure this, is not like in sort of target or simulations.
No, yeah.
Okay, what's the tolerance?
Well, actually, the tolerance is really in that case it on the fiber placement was Oh, good question. I can't remember top of my head like that, but I can find it back and I will send it to you.
I mean, it can be done repeated, like, you know, at the sort of in with the statistic. I mean, this is probably the best of the best I've seen, really, in any method of packaging.
Yeah, but the tolerance on the fiber to the PIC alignment is really in the range of 0.1 micron. You need to have, okay, that is really an active alignment that you can provide, and except you have some mechanical options to make it very specifically. On the fiber tolerance, that is more relaxed, obviously. In that case, it's a few microns that you have in terms of tolerance. Okay.
Okay. Super. Thank you.
You're welcome.
All right. Thank you, Jean-Luc, again. Passing to the next speaker, and I invite Nikolaus Flöry, Business Development Manager from vario-optics, to share his presentation.
Yes, hello everybody. Can you see my screen?
Yeah, you're good to go.
Perfect. So hello everybody. Yeah, it's been really interesting following the first couple of presentations. There were already actually a couple of points which really resonates with me, and which I can only confirm. One of which is that, you know, in this whole packaging and assembly schemes, it's really important to consider the different aspects at a very early stage of a development, and to already take into account the packaging when you actually design a product or design a PIC. So this is also what I want to talk about, as you see here in the title, on electro-optical co-engineering, and hope I can give you some additional insights here. So first of all, let me quickly tell you who we are, vario-optics. So we are a spin-off from a PCB manufacturing company, actually, called Veroprint, and we're located here in the Alps in eastern Switzerland. So what we do is we design and manufacture photonic boards. So we have our own 2 clean rooms. You see one of them here in the background, where we actually produce and manufacture. But as you might know, in the photonics field, many things are custom still. So that's why we're also active in a design and development as well. You see a couple of markets here. We're really active throughout various segments: photonic sensing, telecom, and chip packaging. Again, many photonic parts are really agnostic to the application, such as PICs, or the packaging aspects or packaging challenges are common to many industries. That's why we are also very broadly working. So what are these photonic boards that I'm talking about? Well, I'd actually like to make an analogy to the electronics world. There, I mean, everybody's aware of all the semiconductor chip level developments. There's a lot of buzz around this at the moment as well. But then when you merge, or when you put some of these chips into an actual electronic system and application, we typically go the route of having a board, a PCB, printed circuit board, which is really meant to hold or to package several ICs. Because of course, one IC, even though there is now chiplets and everything, even one IC or one chiplet cannot do the entire job of a product. So this is really what the board level or the PCBs are meant for. Now in the photonics world, we have all these chip level developments as well. And it's been really interesting and exciting because we see a lot of new platforms coming up. Costs are going down, functionalities are going up. So this is really great also for the applications and systems. But still, I would argue that, and I took this little picture here, that a lot of applications are sort of overtaking this board level approach. Not necessarily, this is not necessarily a bad thing. Actually, this is a great package that you see here. It's a great assembly. But many applications till now, they only required, as in this picture here, they required for example, one fiber coupling. So the optical part, so to say, if you look at this package, was smaller than electronics, right? Because there's still, of course, an electronic board used. So what we are working on, what we are manufacturing, are these so-called photonic boards, are meant to sort of fill this missing gap So you can imagine it serves the same purpose. It's a photonic board. It's based on a printed circuit board, but also has an optical layer which can be used to couple and package several optical PICs or optical components. That's the short summary of a photonic board. Now, of course, as mentioned, so we base on a standard PCB technology, which means we can also make use of all the functionalities which has been developed there. So we can have thermal wires, as Peter Bryan mentioned it before. You can have high-speed RF functionality to more than 100 gigahertz. It's actually is starting to become a bottleneck in driving PICs as well, that you get the fast electronics running at the same time. And as mentioned, and this is what we really produce, is an optical layer which is on top of such a board. So this is actually a sort of a PIC platform on its own. So a planar waveguide platform, fully passive, which in our case is mostly based on polymer material. And here I'm really happy again. We've had a couple of talks already about polymer in this webinar, which I really like, because I think it's kind of a trend to see polymer rising. They might have had a little bit of a bad reputation in the past, but it turns out that there are many materials which are actually optically very interesting, many polymer materials, and not only optically, but also environmentally. So, for example, the polymer material we are using is Telcordia approved, so can sustain high humidity, high temperatures. And speaking of temperature, we've heard it before in other presentations, other materials as well can sustain about 300 degrees, which is similar for our material. I stated 270 degrees here because that's a standard reflow soldering temperature, which our material can undergo if it is on top of PCB. Now we are actually manufacturing both multimode and single mode waveguides with different standard processes, similar to any other photonic platform. In the middle, of course, we have also a couple of building blocks of passive devices, splitters, couplers, wavelengths combiners, etc. So in some sense, you can also think of this platform of the opportunity to actually put all the, let's say, boring passive functionalities of a PIC to the packaging, to the board level. Because the main advantage, of course, of using a polymer material is that it's less costly than, say, a silicon platform. So you're not paying for a square millimeter, but more for a square centimeter. You can have larger boards. And so you could also reduce the size of your actual high complex PIC, just limited to the, let's say, active functionalities, and put all the splitting and light routing onto the polymer platform. But actually what's most important on this slide is the right side, so the integration and assembly possibilities that we have. As mentioned, we typically base on a PCB board, but we're also working using glass or silicon as an interposer, as a substrate, which is especially interesting if mechanical precision is required as well. Here are a few pictures. So this is how such photonic boards can look like. And in fact, the word photonic boards is maybe not so true after all, because it turns out that in all of these pictures and projects that you see here, the optical or the photonics part is only part of the story. So the electrical, mechanical, and thermal requirements are often quite harder to meet because most people already focused on the photonics. So this is sort of well established. But as mentioned, it turns out the electrical characteristics can be very important and can be very hard to meet as well, and especially the combination of all of these four domains. And this is why, again, I put together a very short list of, say, requirements which we believe are necessary for a good or advanced PIC packaging, which is, first of all, what we've heard before, that we should really focus on co-engineering, which on the one hand means we should consider the packaging right before the PIC fabrication. There's still ways, of course, to package a PIC or couple to a PIC once it's coming out of the foundry, but you might not be able to get the best best solution after all. And the second aspect of the first part is actually the second point, which really means that you have to consider all these different disciplines. So photonics, electronics, thermal and mechanics, all of this at once, which is really challenging as well. A lot of different disciplines are necessary, but it turns out that this is also really relevant if you want a very well performing packaging or assembly process. And the third part is really what we as vario-optics believe in, and that is that the packaging approach should be scalable in some way, because in the end we all want these great products and chips to end up in high volume applications. And if we're using fibers are great and you will need it at some point, but still fiber alignments typically are linear processes, so the higher the number of ports, the higher the number of effort. Whereas, for example, using our platform, you can structure in one go hundreds, or you could even have thousands of parallel channels. So it's very nicely scalable in that way. And I think that's really important in the entire assembly process, in the entire supply chain, to keep this in mind. Now, one last example how this can look. This is actually a sort of special case out of EU project. So what you see here in the bottom left is a photonic interposer that we designed and manufactured, which is used for the indium phosphide-based 100 gigahertz wavelength selective switch. It nicely combines all these features. So we have a planar waveguide layer, which is used to couple at the same time to 16 optical channels, routes the light, has a fan out inside, etc. You could actually also do on-chip mode conversion, so you can optimize the coupling to the PIC as well as to a fiber, for example. Then, of course, optical interfaces are very important. We use typically our edge coupling or adiabatic coupling to the PIC side, as well as edge coupling to the fiber side. The electric connections are done here on the silicon interposer itself, and later on wire bonded to the PCB, as you see here on the right picture. And actually, so these big wires in this prototype, the red and black one, are for a tech controller, which are used to thermally stabilize this device. So this is what I want to show to you. Overall, we're always looking for partners and collaborations which can either help us expand our technology, add some building blocks, but of course also for partners which can make use of such a platform. So I'm thinking of applications here that have a high port count, multiple inputs or outputs optical, also applications which need high speed electrical interfaces, and overall applications which want to scale to higher volumes. So what we can provide is what I've shown here, these photonic boards or photonic interposers, which I think are one way really to consider if you want to end up with a high performance and also scalable product and application. I'm happy to answer questions, or feel free to reach out if this somehow resonates with you. Thanks a lot.
That's indeed a very interesting platform and a solution for photonic integration. Nikolaus, it is now open for questions from the audience. Just use the raise hand button. All right. The first question from Amir.
Yeah, it's very good project, Nikolaus. Actually, sort of, he mentioned about this, putting these passive components on the board. I mean, why? Like, sort of, it's not like, how long is for example, the directional coupler? We are not saving any area. Maybe off the chip, but the whole product would be a lot bigger. Actually, that's
true. So,
like, and this follow-up is what is the bending radii in your?
So the bending radius is about minimum bending radius between 2 and 5 millimeter, depending on wavelengths and process for Zimmer mode. You're right. You're actually not decreasing the size, but you're reducing the cost, right? And this is actually a main driver for many applications. And you're reducing the cost because you're increasing the area, but on a low cost platform, right? On the polymer platform, as compared to having a larger silicon photonics chip or indium phosphide or whatever. That's what I meant.
Thank you. Anyone else? Oh, I think you mentioned Nikolaus, but I was just wondering again. What are the working temperatures of this polymer?
So it can sustain more than 300 for short times, more than 100 degrees for continuous operation. And yeah, so these standard Tecordia specifications. So 85 for long hours.
Okay, so the most important range it can withstand. All right. Thanks again for sharing this. And I'd like to pass to the next speaker. It will be Josue Parra, the research and development engineer from Ficontec. Josue?
Yes, so good afternoon, everyone. Thank you very much for having me here. So my name is Josue Parra. I work for Ficontec service. Although I'm based in Ireland, I'm in the branch of which is Ficontec Ireland. We are based in Cork, inside the Tyndall National Institute. So what we do at Ficontec? Well, already this slide has been shown at the very beginning of this meeting, but just to explain a little bit more is that at Ficontec, well, we already have more than 20 years of experience working or developing automated solutions for the alignment, assembly, and also testing, and of course, even qualifying some of these assembles. And so we provide, as far as, or as much as I know, the very cut edge in terms of assembling different components, which can be using, let's say, flip chip. And we can assemble different platforms of integrated circuits, like in this case, can be from the normal semiconductor electronic integrated circuits. But our main, let's say, area of expertise is now in the area of photonics. So we are dealing directly with the photonic integrated circuits, which are like based on the platform of silicon nitride, and indium phosphide. So we can assemble the lasers, we can assemble different PICs, and then we can even do the alignment of different optical components. Like in this case, can be the, well, let's say, normal single fiber, can be a fiber array, can be now the even the fiber with the lenses, can be micro lens arrays as well. And then once that we are able to align all of these very with very high precision, like at the sub-micron range, we can also attach them. So we can use different techniques like using UV curing, also some thermal compression, like in the case of flip chip, and as well as laser assisted bonding. And as part of today's meeting, apart from talking about the assembly, we also are going to be addressing what is testing, which in this case, not only we can provide solutions for testing at a single or even package level, which is pretty much the same, but also at the wafer level. So we can also provide some of these solutions. As well as we have some other systems like laser welding, and on inspection, some sorting of components, and some laser bar stacking. So at Ficontec, when I say we provide different solutions, also it depends on the needs of the different customers. As it can be as a research institute, also can be like maybe companies who have like R&D areas or departments where they want to investigate what is the best way to package their prototypes. So we can provide solutions like in this case, on the left-hand side, you can see on this slide, we have like, we can provide lab systems that are more like for R&D, very simple, very accessible from the different sides of the machine. But also we can scale up depending on the needs of the customers to something that is more like production-like system. And even if it requires major production, we can jump towards what is a production automated system. And the very last picture is on the right-hand side is showing what I want to talk a little bit later on. That is an inline assembly of different machines in order to assemble even more complex different components, like more like systems. And what is important here, and it's something also at Ficontec, is the best way we can actually provide a good service and solution for assembly and testing to our customers. It's very important that we understand the requirements of our customers. So understand the process, not only the process, let's say even step by step of what has to be done, but also it's important to understand what are the difficulties that sometimes our customers are facing when they are trying to do that, even at a, let's say, a research and development stage. So in this case, we design our machines for a manufacturing step. And in terms of this meeting, which is for packaging and testing, something that one of the tools that we have developed recently at Ficontec, that we already are using cameras in order to visualize the different components that we have on our machines. So we can develop the tooling that is necessary to handle them, but also in order to precisely assemble these components. I mean, we have already systems that they have like a resolution of accuracy of between 50 to 70 nanometers, but also we can use that, let's say, even for attaching, like in this case, I'm showing this slide, and when we have a component that is a silicon, and then we want to, for instance, place a 3-5 material, like in this case could be like a laser, and then using fiducias, we can use our cameras, like in-gas cameras, and then see through the silicon and see the fiducias and precisely align these two components, for instance. I mean, this is one of the tools that recently we've been adding to our machines, apart from the others that we have from many, many years of experience. And even combining this IR vision, we can even include some of the laser soldering assisted as well. So we can not only visualize from the bottom side, but also we can provide some laser source beam in order to bond the components. So I'll go for my next slide. In terms of testing, we also are providing some solutions for not only at the die level, but also at the wafer level. So as you can see in the picture that is on the left-hand side, let me see if I can, yes, here, if you see this picture. I mean, this picture for sure you have seen it in many other presentations from Ficontec. And in this case, we come from the top, so that would be needed some grating couplers, but also another thing that has been already mentioned in this meeting is the possibility of using these printed structures, so periscope-like structures, and where we can access the components from the edge. But in this case, it's needed this on wafer trenches, so we can then access the side of the components. So there are different possibilities that can be achieved with already, let's say, with our machines. Even for that, as you can see, we were working already with Vanguard Photonics. Even Vanguard Photonics, they offer the machines for doing the printing of the periscopes, lenses, and these photonic wire bonds. And they are even using, let's say, our platforms of our machines. So it can be either that somebody gets a Vanguard Photonics machine, which already even has this software that we have for Ficontec, or even let's say get the polymeric components, like in this case the lenses and the periscopes, and then maybe attach these components to our machines. And then we can, I mean, the customers can access and let's say their devices at the wafer level as well using our systems. Something as well that is important to mention is like right now we are talking about maybe at some point like it sounds more like an R&D research that of course is still ongoing because still we are lacking of different standards for let's say not only for assembly and testing but also for the machines that they have to perform all of these activities. But what is important as well to consider is like the production itself. So there are companies they already need to fulfill certain number of deliveries of with the current technologies. So at the moment, we offer also the possibility of, let's say, assembling different machines. So in order to really do different assembly processes, like we can here fitting the components, then they go along the different machines that are interconnected and with different assembly processes. And also, as you can see here, not only assembly, it can be like maybe to capture, read the stamp, analyze data, and then even put laser soldering, whatever is needed, sorting, anything. And then at the end, we just get the product. And in addition to that, what is important as well for companies who are interested in, let's say, ramp up their manufacturability is that also we offer, apart from the normal software that we have at the moment in our machines, complementary machines that they can, software that can even at real time monitor what is happening in the process already, or the assembly process. I mean, that's the testing process. So we use some machine learning and AI, so we can then complement this. And as the assembly process go along, even the customer gets information of how to improve the process, how to make it faster, because even it is possible to correct and rectify if there's a problem with the assembly, as it is already in line going with the first production. So it can be retro feedback and then improve the process as it goes along. So for instance, this already has been used for the production line of big companies producing transceivers, cameras, and LiDAR applications. Also, well, at Ficontec, apart that we are always interested in improving in terms of technology for assembly and testing, we also are aware that we have to provide very good service to our customers. And in order to do that, we are now opening more different branches, like in this case, the branch in Ireland, in order to take to our customers as close as possible of where they are around the globe, somewhere, some lab, some point of contact where maybe they can approach easier rather than being concentrated in one place. Like in this case, the headquarters are in Aachen, Germany. And then we can help them to find the best solutions for their assembly and testing. So thank you very much. And if you have any questions, feel free to ask now or even later, feel free to reach out. Thank you very much.
Thank you, Joshua. Great presentation. I'm sure there are many people in the audience who already use your machines.
Thank you.
So we have a time for just 1 or 2 questions. Please go ahead. Raise your hands. Let's start with Marco from ATNS.
Yeah, hi, Marco here. Are you thinking, will this machine provide a full electro-optical testing capability, or some other equipment must be seen in order to fully test the device?
That's a very good question, and thank you very much for asking that. Because let's say these machines that we are already providing, they have capabilities for doing the optical and electrical testing. However, as let's say the complexity of the different systems increase, also we have to find out or investigate what new ways of doing things. Like in this case, something important that Peter O'Brien was mentioning is about the assembly, like placing these micro lenses, and then it is possible to reach out on the wafer with an optical probe. But also it's important as well to be able to access also from the bottom and to power up all the different components on a wafer, for instance. So in this case, even Peter O'Brien mentioned about this project, Photonic Leap, where Ficontec is one of the partners. And Ficontec, we are working along with the Technical University of Eindhoven with Sylvester Latkowski and Shigo Kongo. And we are actually working towards the development of better probing, let's say hybrid probing at the wafer level solutions. So in this case, exactly what you're mentioning, like being able even to test optically and electrically, let's say, components on a wafer.
Okay, thank you.
I hope that answers your question, Marco. Anyone else? Because if not, I would suggest that we move to the next talk. Thanks again, Josue. The last speaker of the session, as we moved from packaging all the way to testing, is Richard Furey, the director at Yelo. And we're very glad to have you, Richard.
Okay,
whenever
thanks.
you're ready.
Can you see my presentation there?
Yeah, you're good to go.
Okay, thanks. So thank you, holding everybody back for the end of their afternoon. So I work for a company called Yelo. We manufacture burn-in and life test equipment. The primary business is the design and manufacture of systems. Typically, I mean, we've got three main ranges. A low power, less than 1 amp burn-in system, covering about 1,000 devices. A low power, similarly less than 1 amp, but covering 5,000 devices. The main difference between these two is that the Y1000 offers air cooling only, and the Y4000 also offers water and tech cooling. And then we also do a high power system, which goes up to 300 amps. And needless to say, that is water cooled. So those are systems we manufacture. But looking at what we actually do, I mean, the first question is, what is life test? So life test is what you would do normally at the early stage of device development, where you're trying to prove the long-term reliability of your devices. It's sometimes also used as parallel wafer qualification. So you normally do life test when you're developing products, but you might do an ongoing sampling process from wafers. That ties in a bit with what Peter was saying, where you might put some test devices around the edge of the wafer just to qualify the wafer. It's also used to find a sweet spot when you're going to do production burn-in. What is the optimum current and temperature to age a device at? You want to age it quickly, so you have a short burn-in, but not so quickly as to damage through other mechanisms than the normal failure mechanisms. Life tests typically will run anything from 2,000 hours to 8,000, depending a little bit upon the product. Burn-in, on the other hand, whilst it might use the same equipment, is used as a production technique to identify faulty or early life failures. So in burn-in, what you do is you stress the device electrically and thermally. And again, based upon what your earlier studies are, you will have chosen a temperature very rarely above 150 degrees C, and will lie anything from about 85 to 150. You may also overstress in terms of the current drive, which can also speed up the aging process. What you're trying to do is to make the failures due to the manufacturing process of the laser diode in the first place occur much earlier in the life cycle, and particularly before you've spent money packaging. So that is the principle of burn-in. Burn-in times anything from 2 hours to 168 hours, depending upon what the product is, how sensitive it is. I mean, if it can stand a lot of abuse, you can get a shorter burn-in. The problem about burn-in is when should you do it? You start at a wafer level and you land up with products in the field. If you do your burn-in at too early a stage, let's say you do it at wafer level, you may not capture some of the failure modes. If you do it too late, when you spend all your money hermetically packaging it, you've thrown away a lot of money in that process. Typically, we find that at the chip on carrier stage, so sometime after it's been singulated, but before it's been stuck into something more expensive, is the optimum time for burn-in. We are looking at wafer level probing for burn-in. It's slightly different from what Ficontec do, because you have to, because you're aging the devices, you need to be driving many of them at the same time. You can't do single devices at the same time. You need to be doing at least 5,000 in a group to make it worthwhile. And even then, you're going to have to step and repeat across a wafer. We have a big project doing that at the moment, but as I say, the challenge I keep on going around is obviously some of the failure modes are related to the original laser architecture, but some are also related to the subsequent processes, the singulation, the bonding down onto a carrier, the wire bonding, can all potentially introduce failures. And I have to say, I don't know many people that know exactly what all their failure modes are. So that's a whistle-stop tour. I was conscious I was at the end of the line. I didn't want to keep everybody hanging on too long. We're always interested in collaboration. I think we may be certainly talking to Icon Photonics and Nanoscribe, I think, who have things that they can offer us. And indeed Ficontec as well. But we're also interested, I think, again, as Peter said near the beginning, the earlier you look at how you're going to test things, the better. Somebody comes along to us and they've already decided what their breakout is going to look like and what their pads are going to be, and you say, well, that's going to double the cost of doing your burn-in. So early talking about your process is important. And that's me.
Great presentation. Thank you very much, Richard. I'm sure this will raise a few questions. So it is now open for the audience. Please use the raise hand button. I was actually Antonio, go ahead.
Yeah, I have a curiosity because some of these diodes are using applications like medical or space. Are there specific regulations to make these kind of tests for the components that are using this, let's say, quite strict applications?
As far as I know, not at the moment. I mean, Telcordia have obviously in the telecom side, well-established, processes and protocols. It doesn't seem to be as well established in the other fields like medical, etc., although it should be, but it isn't at the moment.
Okay, thank you.
Okay, anyone else? Richard, I was wondering, what is the typical cycle time for a burn-in test?
Typical is probably around 12 hours. Would be a typical cycle would be to do an LIV of the device at 25 degrees C, raise it to 85 to 100 for about 10 to 12 hours, then bring it back down to 25 and do a final LIV. And then you typically look, well, obviously you get dead devices and that's easy, but most people look at the shift in ITH as being a good measure of device performance.
All right. That could be possible to do it both at the wafer level and then later at the chip level, right?
Yes, I mean you could do a burn-in at wafer level, which might exclude a lot of the semiconductor issues, but would exclude some of the process manufacturing issues. But you might then get away with a much shorter burn-in at the subsequent stage.
Okay, that's very clear. Well, we're unfortunately already at the running out of time, as it's already 5 p.m. So, okay, I would like to thank you, Richard, again for the presentation, as well as all the other speakers of today's seminar. Just a few final words before I close this session. So we're very glad that you joined us for this EPIC Online Technology meeting on PIC packaging and testing. We had the pleasure to hear 7 presentations today from Tyndall Institute, from PHIX packaging, from Nanoscribe, Photonics, as well as vario-optics, Ficontec, and Yelo. I'd like to remind you that this is a very important one, but not the last OTM that we're planning online. Here you can see the list of upcoming events organized by EPIC, and just in a week from now, we'll hold a similar seminar on the Earth observation. And as well, in December, there is an online technology meeting dedicated to photonics for food and beverages. We'll start also next year, 2023, with the online technology meeting on metamaterials and meta lenses, and followed up by laser-based manufacturing for implants. And later in February, there is also bioimaging topics and quantum metrology and quantum sensing that kick in. I'll take also the opportunity to thank the team of EPIC, and remind you that EPIC is always happy to support you with technology consultations, market reports, opportunities for networking, and accessing new markets, mentorship in photonics, HR support, and investment. With this, would like to just thank our sponsors again for supporting this event. And we're 800 members already at EPIC, so we're always welcome to join us. Thank you very much. And goodbye.
Thank you, Ivan. Goodbye.
Thank you.
Bye, everybody. Thank you.